did something different, and we can practice, we can have a what if, kind of a model, and then we can try to pick the best one of those courses of actions, and then apply that learning to the actual physical oil field as we go along. So keep that idea of this sim oil field as you go through this, and I'm going to show you lots of different aspects of exactly how we're trying to make that happen. So the next slide.
Okay, I haven't started the slides yet, I'm sorry.
Very good, that's the right slide. So in Chevron, we call our digital oil field program iField, where the I stands for integration. The other companies have similar programs, they call them different things. It kind of doesn't matter what the name is, but we're all trying to get this idea of marrying together digital surveillance of what's going on, our modeling of what the asset is capable of doing, and all those pieces that we believe is kind of the next kind of breakthrough, really cool thing that we can do in order to try to create more value, but at the same time operate in a much, much better fashion than we can today. This concept of managed by exception, which is kind of the first bullet there, is this model, the idea that I talked about a little bit, which is trying to marry what the model predicts would be your best possible result versus what your actual physical environment is trying to do. So therefore, instead of just managing by reacting to safety alarms or things that could go wrong, we're actually trying to manage against what the model predicts we could do versus what is really happening. And the comparison of those two in as close to real time as possible is how we want to try to manage the game, how we want to try to manage the oil field asset. Now clearly that involves a great deal of collaboration. As I'm going to get into a couple of slides that just shows you how difficult that collaboration could be, where all the different actors in an oil field kind of an operation might be at. So the collaboration kind of concept is a very important part of it. And clearly the idea of bringing the decisions to wherever the experts are. Now, sometimes the experts may be really close to the piece of equipment. Sometimes they may be halfway around the world. So this concept of see the right information and bring it to the experts is a really important part of this. And we want to try to make decisions as quickly as appropriate. Not everything is real time. Not everything is kind of by the second kind of operation. Things that are, there are certain things whose kind of cycle time is hours or days or weeks, and whatever is the right kind of time to make a decision that is relevant is what we're trying to get to. And clearly these maintenance duties, project duties, or whatever it is as they go around doing this, but obviously it is their safety and their actions that are probably the most impactful as we go through this. And we want to try to support those people to the best possible way. They may not have the deep expertise in a particular engineering field, or they may not be the scientists who understand the reservoir or whatever, but they are the actors that are turning the valve. So our kind of wireless environment, if you will, that we have to put together within our world, and we do for some of this use the public internet. So that we don't build all of our own networks. They're not all private. Some of them are very public, and we just use those. But we have to bring together that network, if you will, that's out in the field, that's out on that network. We have to bring that back to our headquarters offices. And then at the same time, we have to have the ability through the internet to bring in the experts wherever they may be in their own offices or another part of the globe, on another job, or whatever it is. We have to bring them all together in this virtual collaboration session, at least for the period of time that they need to make their decisions or do their analytical kind of work. So this connectivity that we have to do is pretty amazing, because we are going in a lot of places where you don't have a Starbucks. You can't just go in and have a hotspot there. We have to take our hotspots with us out to where we have that field operations piece of it. So we actually are building and running a lot of that first mile kind of connectivity where we have to take the network and we have to have the connections with it. Next slide. Let's build this slide out, which talks about the pieces of this environment, military and homeland security and people like that are trying to do in their operations as well. Increasingly, the military runs a digital war. if you will, or a digital series of operations is what they're trying to do. They will have remote surveillance, maybe from manned aircraft, maybe from passive posts, maybe from these predator drone, kind of robotic aircraft that flies around gathering information. But that has to be connected back to headquarters, to logistics, to where the troops are, where they're going to dispatch that. And all of this has to be kind of an integrated environment to allow, obviously, the military operations or the security operations to be run in the most effective possible way to ensure, the success of that operation. So there's an awful lot of this kind of technology that's being, developed and promoted by, these kind of industries, if you will, that we're also reusing and we're going back in and trying to figure out how to apply to our problem, which is the next slide. So, which is our integrated environment that we have to have, all the way from sensors downhole to the producing facilities, the headquarters offices, and then the distributed nature of our industry around the world where the experts may lie, where the equipment, where the replacement equipment might be, or whatever is the, kind of expertise that we need to build. And we need to build it on an as-needed basis. This isn't all the time, always on, dedicated to you. Dedicated and leveraged all, not dedicated at all, but leveraged around a number of different assets as we have, and we just pull them together when we need them for a specific problem. So next, I'm going to talk a little bit about what we can do in terms of what information we can acquire. Again, this is another Gulf of Mexico deep water platform where we are producing one of our major assets in the Gulf of Mexico. But we not only have sensors that are on the equipment on this platform, but we increasingly are putting sensors down the well, near the reservoir face, so where we can measure pressure, temperature, other chemical kind of readings and measurements in order to try to get a more and more accurate picture of what's really going on with the reservoir. So that these are looking more and more like plants, like refineries, like complex manufacturing factories that just sit out there on top of the oil field. So we have, you would think, well, how many sensors might you have on a platform like this? It's now from the tens of thousands to the hundreds of thousands of data points that we can measure, including several thousand, which would be in wells, maybe as much as 10 to 15,000 feet below the surface, that are all part of this fully instrumented facility. This is where we can collect data in almost near real time. You can almost set your sampling interval to seconds, to minutes, to however effectively you want to gather data in order to try to use it. Our big problem is not getting data. Our problem is trying to figure out how to use all of that data when it comes back to the human or to some automated process or some automated. It's helping us manage all of these sorts of things. So I'll give you one example of how we're trying to take these sensors downhole next to the reservoir and actually do more than just collect measurements, but do something about it. Next slide. So this talks about something, this Agbami field. It's one of our new fields, probably our most modern and our most automated and certainly the ones that we have some of the most measurements on, but it is offshore Nigeria, in deep water off the west coast of Africa. IWC is a term that's called, it's an intelligent well completion. So the intelligence is having to do not only with the sensors that we put downhole and this little carly gather information about what is happening down there, but with these smart completions we actually can send commands back to it, essentially remotely control some of the equipment that's at the bottom of that. For example, if a producing well is producing water and not very much oil, we can, and of course we want the oil because when we produce, we don't want the water because it's kind of a waste product. We can shut off the completion there and not allow the water to enter the well. So therefore, we don't have to dispose of it later. We keep it in the reservoir and we reduce, kind of the impact that we have. In other places where we actually inject water at the flanks of a field in order to push the water towards producers at the center of the field, we can actually control which zones are most efficiently taking the water and pushing the oil towards the producers. So it isn't just a one well view of the field, it's almost patterns and whole well view of the field. And in this particular complex operation, we are injecting water at the flanks, we are taking oil from the center, we are producing gas from the well, but it is recycled to go back into the facility because we don't have a commercial use for the gas. We do not want to flare it, we don't want to have that environmental impact, but we're managing all of those processes through almost this remote control and very well instrumented and sensed kind of environment that's actually 2 miles deep in the ground. Next. So now my last kind of couple of slides as I finish this off, I'm going to talk a little bit about some of the advances that we're trying to do to help manage all of this information that comes together. Clearly one of our big problems today is information overload. It's just too much data coming in. How could the human being know what to look at? You as an engineer or looking at analysis, you know, there's just too much of it to digest. You wouldn't know which problem, where the problem was, or what the kind of problem it was, or what you should be spending your time on. So we spent a lot of time in this area of, you call it boards or cockpits or portals, or there's all kinds of different kind of names for them, but we're trying to make them more and more intelligent. And in that sense, we're trying to show the information in some kind of context. Here's an example of how we're showing the information around different sensors on a piece of equipment, and then plus a graph of how it's changing over time. The kind of the red and green and black, you know, kind of scorecard is actually a piece of technology called Tree Map, where we actually not only use colors, but sizes and shapes and even animation. We can have blinking light. Helps direct the human's eye towards the right piece of information. We're having the information trying to go get the human, instead of the human trying to recognize what the situation is that they were trying to work on. This is commercial technology. It's actually used by a website called Smart Money to track how stocks and bonds are changing in the financial marketplace. Here we're using it to try to signal to the control room, if you will, the support center, you know, how much oil, or in this case gas, a well is producing. Is it producing what it's supposed to be? That would be a green light. If it's doing less, it might be a red light. If it's severely, you know, that way, the size of it would show the quantity of gas. So there's a lot of information that you can show to the human operator, but you have to be very clever about it. You have to try to think about what is it that will attract the attention of the human and do the right kinds of things, and then know what to do about it. So when we get to what to do about it, that's the next slide. So here is one of those examples of a field, like I said, talking about being waterflood. So we're talking about hundreds of wells. I think at Lost Hills, which is a Central Valley of California field, where I think there's 300 or 400 wells involved in the whole operations. And we inject water along the flanks, and we produce oil along the crest of the structure. But we have to keep all of that in sync. We have to understand, we don't want to just ground because it's expensive, and then not produce oil from it, called water cycling, and just produce it again. We want to try to, again, balance or get the right, you know, kind of connection between all of these different things. And it requires a lot of different views of the data, a lot of different displays, a lot of different, and they have to be interactive. I mean, this data now is changing. The red lights and the green lights and things are changed almost on a minute-by-minute basis from information that comes from the field. Some of it's direct measurement. Some of it's a calculated kind of quantity that we go through you know, some work in order to try to say what the right condition is. And then on more analytical basis, once we don't have to act so quickly on, we will want to take, you know, a lot of different views of graphs of time, graphs of different quantities versus each other. And there's a lot of different kind of this engineering analysis that goes along. But we're able to do this instead of just a once every 6 months historic kind of study, but almost a real-time kind of a basis of what is actually going on and keeping up a lot closer to the reality. Next. So any of you who want to be graphic artists or talk about, games have to do the same kind of thing, websites have to do the same kind of thing. There's just too much information out there, and you have to be very clever about how you display the information to attract the viewer's attention to it. Whether I'm trying to sell something on eBay and I want you to buy my thing versus somebody else's, or on a website, or to keep you from here, the operator, to pay attention to the right amount of things. This one here is around a very complex process. It's our kind of classic example of all of these systems coming together, where we are combining what happens in a well, what happens in the reservoir, what happens in the producing equipment, and we're trying to look at them and kind of see all where the activities are, and around, your well may be working just fine, but you happen to be producing too much wastewater. And the wastewater plant in the facility is overwhelmed. It has too much. It can't handle anymore. So you can't make a change to the equipment. You have to make a change back at the well and what it's producing. And it's the interdependence of all these different systems is our most complex and complicated problems. If we can solve these, we can unlock hundreds of millions of dollars more value in our existing operations and have much less of an impact on the environment that we're trying to work on. So next, and the good news is this is my last kind of content slide. I'm going to stop talking here in a second. I talked about games, and while we're using this gaming technology for very serious purposes, there actually is a game that you can go out there and play to get a little bit better feel for, if not so much oil and gas operations, but from the kind of energy consumer side of this, in a game that we've actually put out on a website called Energy Bill. The website is willyoujoinus.com. It's a Chevron kind of hosted site. But if you're ever interested and want to play a game about this, if you want to play the role of a city planner who has to plan all of the energy uses for your community, you go on this site, you click on the Energy Bill kind of section of it, and you have the opportunity to go plan all of the energy use. Where do you buy it from? Do I want more renewable power? What you have a budget to go from. You have different supply constraints. You have all the rest of this, but you can put yourself in the seat of a city planner trying to provide energy to keep your community running, all on this site for free. Doesn't cost anything. There's no sense of housing slide here. It's just kind of our cartoon of the iFeel program. If you go to the last slide. Okay. So now, any questions? Anything that you'd like to know a little bit more about? And Julie, if I can have the picture of the people instead of seeing my slides now.
All right, so we have a question in the back. Let me go. So this is Adam.
How close to production is the simulated game going to be?
Okay. If I heard that, you said, how close are we to some of these simulated games to reality?
Yes. Or
today we can do. Sorry, did I interrupt you?
No.
We can do parts of the game, if you will. We have models of how a well behaves, or we have models of how well a reservoir behaves, or models of how equipment behaves. And so we can play those games where we have a model of what should happen, and we have surveillance and equipment and sensors on what is happening, and we can compare the two. Those we are doing right now, and we've got a number of instances inside Chevron where we're doing that. The game we haven't yet solved is how they all work together, that kind of last one. That's where we're just kind of bringing up information from those different functions and try to to look across those things. But we haven't built the most complicated game, we built the simpler games. Stand up, I just need to hear you.
Okay. How accurate are the simulations that you guys produce?
That's a really good question, because no model is perfect, and we know that, so we never get to 100%. it really kind of depends how accurate the model is on, how much, well, first of all, effort we put into building the model. We have different kinds of models. We have some that are very, very sophisticated and that literally take months to build. And we have others that are more kind of black box sort of things that don't take effort to build, and the results are probably a little bit less accurate. So it varies depending on what our problem is. But usually, they can be as accurate as, say, 5 to 10% right, 90 to 95% right, or we could, sometimes we can only get in the ballpark of maybe say we're 60 to 70% accurate with regard to these things. That's one of the reasons we need a very adaptive environment. We need to continue to train our models, as we call it. Always train the model on some piece of real data. But then we're working on ways to have adaptive models where the model gets smarter and smarter and smarter based on the real data that's actually training it, so our forecasts get closer and closer. But we clearly want to get into the place to be within a few percent.
Thank you.
Anybody else have a question? No more questions?
First speaker after lunch.
Yeah.
That's always a tough one.
All right, well, I think they're
Well, I sort of have a question, I think it's kind of similar to the one he had. I'm just gonna ask it anyway. Like, from the games that you do have, what are the results that you expect? Like, have you been successful? Are you guys satisfied with what you have achieved, basically?
That's a good question, because at the end of the day, it's not just game playing, it's got to be of economic benefit. But an awful lot, not every project is successful. We're still in kind of a learning, kind of mode, but many of them are. And we met the, economic results of improving. I'll give you just 2 or 3 kind of examples of things that are real cases. We've already done them. We've already measured the results. In a gas field in East Texas, we've improved production by almost 5% without drilling another well. All we did is to operate those wells more efficiently. We had another case in, this one was near Bakersfield, where we were able to save several $100,000 a year in producing steam. The oil in Bakersfield is very heavy, very viscous. And we have to inject steam in the reservoir, not water, to lower the viscosity so the oil will flow. But to do that, we have to burn oil to create the steam to put in the reservoir to produce more oil. So there's kind of this issue. But we've been able to make that process more efficient, save several $100,000 a year on one field in order to burn less fuel to create that steam. And by burning that fuel, we can both sell it, and then we have the less emissions in the steam generation plant that sits on the surface. Another one, again, has to do with reliability of equipment. It's, a traditional operation would almost essentially have sensors to wait till a piece of equipment failed or broke. And then it would safely shut down, and then we would go make the repair, the fix, or whatever. But if we can figure out when that equipment is starting to go bad, when something is starting to break, before it's actually failed, the repair is much less expensive. So the ability to go in there and catch equipment before there's a severe failure, do it in a maintenance kind of a schedule instead of a major project fix schedule. Again, we can save an awful lot of money by keeping equipment up and running longer than we would have otherwise in terms of how a traditional operation might have done. But clearly we feel that we've already seen value in the tens of millions of dollars through various different projects, and we think the potential value is in the hundreds of millions of dollars.
How did you develop your whole gaming thing? Did you actually have actual gamers develop it along with like your engineers, or how did you develop the whole idea and the whole process of everything?
That's a good question. Most of the people doing the development of these things are actually our engineers, not those folks particularly on gaming. Although we do have a project going on right now, this virtual reality kind of environment where we're working with a company who has gaming programmers. So we actually are getting into the space where people who write games for a living are helping us do some of these things. But that is particularly in the virtual reality kind of space, where we're trying to create a second life kind of environment to try to do this. Most of the rest of these are engineers who are very schooled in a lot of their analytical techniques. And we were building models before. The problem is the models weren't connected to the real environment, and they weren't very adaptive or weren't very responsive to what was going on. So most of these are, I mean, we got IT programmers sitting working with petroleum engineers and facility engineers, and they're just building more and more in this space of taking their models into this kind of game-like kind of way of using them, and then linking them to the real surveillance, and then doing the rest of that. But it goes all the way from a regular IT programmer, a regular petroleum engineer, all the way into folks who are using gaming engines in order to build these models.
Thank you.
Go ahead, Sybil. Let me kind of
How did you develop your interest in this area that you're working right now?
It's an interesting question. My background, as you can probably look from the gray hair in my beard, I've been around for a little while. I've actually been with Chevron for, I'm in my 34th year with the company. So I started somewhere back in the 19th century. You were supposed to laugh. I have my basic degrees in geophysics. So I was involved in an awful lot of trying to understand the subsurface. And there, we were always building models, mental models, mathematical models, whatever it is, of the subsurface because we couldn't see it. From that very beginning, I'm a conceptual physicist. My math wasn't as good to be a real physicist, so I ended up being a geophysicist. And it was always kind of this model building kind of mode, and I spent half my career doing that. Then, through reorganizations in the company and different opportunities, I moved over to the IT side of our business, still supporting upstream, but then also getting on the digital and how the IT parts of it work. I've done some programming, but you wouldn't want to see my code. It's very awful code. But I kind of got a chance to marry the earth science piece of it, the IT piece of it, and then about 8 years ago, when Chevron's iField program started, I had the opportunity to work at the early stages of it and kind of bring all of these things together, because my interest is actually the integration of those things. So different people have come at it here from a more IT background or just this engineering analysis model building background. Our program is really done, it has a lot of different kind of people involved in it. But one of the most exciting pieces now are the young engineers who are coming, who are just incredibly more digitally literate than the old engineers ever were. And they just kind of expect the IT stuff to be there. They are used to the social computing technologies. They're used to the gaming technologies, because that's what they grew up with. And they just say, well, why can't I do this? And that kind of an idea, which wasn't there when I started with the company, is now more and more taking this asking, why can't I do this? Instead of, gee, this would be a neat thing to try. But, different people, different backgrounds. I shared a little bit of mine. Mine's been the long journey. There's a lot of other people whose journey is a lot shorter, and they've gotten to the same place.
With all the projects that you're doing, like with this new system, who provides the budget? Like, because
where do you get the money?
Yeah, like the previous speaker has said that they didn't want to fire the people, and so
Our different business units, we have to sell the value to them, and they come up with the money. It's not centrally funded very much. It's not funded from the technology company or wherever. It's really funded from the business units who say, I want you to do this project for me because I think I can get this value from it. And so, we've got probably more than half of our 14 business units who have funded projects, started projects, are putting money into this. I work in a headquarters group, so I'm kind of involved in a lot of the coordination and the marketing and the communications as well as the design pieces of this. But most of the money comes from those business unit managers who see a real value in what they're trying to do. Now, so some examples. Compressors are very important in our gas operations in order to try to compress the gas and put it into the pipeline in an efficient way. But monitoring those compressors is a huge equipment, a problem that we have. When those things go down, we lose production, we lose an awful lot of value. So one of our projects is monitoring the compressors that we have, very big pieces of equipment. Another one of them is trying to get information, not only collect it efficiently from the operators as they go around their daily chores, but get directions and plans and things back to them so they can efficiently kind of execute a task they may not be trained on. So we've got that kind of a project going on. Monitoring well performance, monitoring reservoir performance in training these reservoir models with real-time information. Those are our active projects right now that we're working on. But the money comes from the business units who make the money.